Hello, everyone. Welcome to Vivid Technology. Today, we will be discussing some exciting topics regarding the RLP technology. What is RLP technology? How does RLP technology work? What are the technical and strategic advantages of RLP technology? Let's dive in. First of all, RLP stands for Repeating Layer Process. This innovative mathematical algorithm leverages a common structure found in the majority of manufactured products across various industries, including automotive, energy, pharmaceuticals, food, and more. The best way to explain how RLP technology works is through a case study. In this case study, we will discuss how to build a system that assembles a battery module. The battery module consists of 24 cells, 12 positive cells and 12 negative cells. We need to produce and introduce a cell every 4 seconds, as opposed to traditional systems that can prepare and produce a cell in under 2 seconds. Our system availability will range from 92% to 99%, but for simplicity, we will use an average of 95% for our calculations. Operational times for this case study are 21 hours per day and 240 days per year. Components will be categorized into 2 types. Non-repeating or overhead layer components. These components appear only once in the lifetime of the product, such as the case and the bus bar. Repeating layer components. These components are introduced repeatedly to the product, such as the positive and negative cells. Machines will be defined to prepare and introduce every component to the module. Additionally, an unload machine will be built to unload the complete module. Battery cell machines will be built to perform the necessary operations to prepare the cells for introduction into the module. The operations listed here are some of the common ones, but they can be adjusted depending on the product design. Here, we will learn how to calculate the cycle time between unloading a complete module and unloading the next one. We will use 3 parameters: green, blue, and yellow. Green parameter represents the number of repeating layers required to complete the module. Blue parameter represents the number of layers that can be introduced to the product with each pass around the system. Yellow parameter represents the RLP cycle time, which is the 4 seconds we mentioned earlier. By dividing the part repeating layers by the machine repeating layers, we can determine the number of passes the part needs to make around the system. Then, by multiplying the result by the RLP cycle time, we can calculate the total cycle time for a complete module. As we see in the motion of the system figure, this is how the carrier travels through the system to gather the necessary components until it reaches the maximum number of cells. Since our product requires 12 layers, and this system only supplies 1 layer per pass, this means we need to loop around the system 12 times. By multiplying this number by the cycle time of 4 seconds, we end up with a total cycle time of 48 seconds, or 75 modules per hour. It's important to note that this system has a manufacturing cost per unit that is equal to that of the traditional system. By adding only 2 machines out of the original 5, which is 40% of the system, we can significantly enhance our production capabilities. This expansion will increase the denominator in our formula, cutting the cycle time in half and doubling the production capacity to 150 modules per hour. It's also worth mentioning that by adding only 40% of the system cost and footprint, we can achieve a 100% increase in system capacity. This results in lowering the manufacturing cost per unit to 70% of the traditional method. Adding 2 more machines will allow us to increase capacity by another 100% with an additional 40% system cost. This further reduces the manufacturing cost per unit to 60% of the traditional method. By adding another 40% of the system, we can achieve a 400% of the initial system capacity. This further reduces the manufacturing cost per unit to 55% of the traditional method. Adding 2 more machine layers will give us 600% system capacity for only 300% system cost and footprint. At this point, our manufacturing cost per single module is reduced to 50% of the original cost, which is equal to 50% of the cost with a traditional system. This expansion will continue as we keep adding more layers of machines, whether they are repeating or overhead layers. Let's talk about the new manufacturing standards introduced by RLP Technology. Production capacity. With RLP Technology, we can scale production capacity to over 20 times the initial capacity. That's a game changer. Availability. Our system availability ranges from 92% to 99%, which is a huge improvement over the traditional maximum of 85%. Imagine the efficiency gains. Cost per unit. We can produce at under 50% of the cost compared to traditional methods. That's a significant cost saving. Real estate. The RLP system takes up less than half the space of traditional systems. More room for other operations or even expansion. Time to market. We can get products to market in less than half the time it takes with traditional systems. Faster production means quicker profits. Let's explore the strategic advantages of RLP technology. Technological leadership. RLP Technology positions our nation as a leader in advanced manufacturing, showcasing our cutting-edge capabilities. Economic growth. By creating high-tech manufacturing jobs, we boost local economies and provide new opportunities for skilled workers. Global competitiveness. This technology enhances our nation's dominance in the global market, making us more competitive on the world stage. Innovation hub. RLP fosters innovation and attracts international investments, turning our nation into a hub for technological advancements. Critical infrastructure. It supports the development of key technologies like EV batteries, chips, solar panels, and pharmaceuticals, which are essential for our future. Strategic autonomy. Maintaining national control over essential manufacturing technologies ensures our strategic autonomy and security. Thank you for watching.